Welcome to Math 1324. This is section 7.4. We're looking at how do we count. Now you might think, well, that's easy. You just put all the things down on the table and start counting them. Well, sometimes maybe you can't actually list all the possibilities because there's too many of them. So we need a way to count. And in counting, the first thing we need is this symbol, which is 8 with a little exclamation point. This means 8 factorial, and the bottom 4 factorial. Well, factorials are fairly straightforward. 8 factorial just means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So whatever number is showing, you're just going to multiply all the way down. 4 factorial is 4 times 3 times 2 times 1. And so if we wrote them all out, then you could simply cancel these items. A faster way is just to do 8 times 7 times 6 times 5 times 4, and we know it's all the way down, but I already have 4 all the way down, and so those would cancel. And so what do I have? I've got 8 times 7 is 56, 6 times 5 is 30, and so the multiplication would give me 1680. Now the reason we need this shortened version is, well, it's not always easy to multiply everything out. For example, what if I had 50 factorial over 48 factorial? Well, I don't want to have 50 times 49 times 48 times 47 and list all this out for all 50 items when I can just do 50 times 49 times, and then I know it's going to be 48 and everything under it. So if I put that over the 48 factorial under, I simply can cancel these two, and then to evaluate this, it's just 50 times 49. In question 2 here, we have 15 factorial over 4 factorial times 15 minus 4 factorial. Alright, well, what is 15 minus 4? 15 minus 4 is 11, so that's 11 factorial. So let's see, I'm going to take the top and write this as 15 times 14 times 13 times 12 times 11 factorial. And I know I can use that to cancel the 11 factorial on the bottom. I'm going to expand the 4 factorial as 4 times 3 times 2 times 1. So let's see, 4 times 3 is 12. That goes away quickly. And 2 goes into 14 7 times. So I simply need 15 times 7 times 13 to give me 1365. All right. In this question, I'm looking at trying to figure out, do we have something that's called a permutation, a combination, or neither one? A permutation, order matters. Okay, so let's write this down here. Permutation. Order matters. Now, what does that mean that order matters? It means that the way I list something makes a difference. For example, if I've got 3 items and I know that one of them was first place, one of them was second place, and one was third place, then the order matters because who got first place is better than who got third place. But if I just throw any 3 items on the table, how I look at the 3 items makes no difference. And that's what a combination is. So a combination, order does not matter. Now, it doesn't help because we have locks, and the locks are called combination locks. But if you think about a combination lock, when you try to open it, even if the combination is 5, 20, and then 10, how you turn the thing to get the 5, the 10, and the 3 makes a difference. So that's not what a combination is in this sense, and in this sense a combination does not matter. If the order you do something makes a difference, then order does matter. Okay, so let's see. As each roommate will have a specific day, okay, 7 roommates pick which night of the week they will cook dinner. Okay, so I got 7 people. Each night of the week they're going to cook dinner. All right, well, the night of the week matters, and the days fall in a specific order, so the order is important. And so this is a permutation, right? Because who cooks on Monday is different than who cooks on Wednesday. So if I just say, oh, I don't care, I need 3 days. Well, then just I need 3 people to do those days if I don't care about which day is which. All right, and in our last problem here, I have a pool of 7 people to pick from, and I'm going to pick 3 people. So 7 total in this pool of people, and I'm going to pick 3 of them. Okay, so why is there this difference in number? Okay, so how many ways can I just pick 3 people where the order of the people I pick make no difference? I just need any old 3 people. Well, if order does not matter, we have this formula for combinations. N is the total number of people that we've got. So here's N, and I'm going to pick from that sample R of them. So in our case, I've got 7 to pick from. I'm picking 3 of them. So 7C3. So then I just evaluate this like we did before. 7 factorial, 3 factorial, 7 minus 3 factorial, which gives me the 4 factorial, and then simplify to get 35. In B, order does matter because I've got president, vice president, and secretary. Who gets which role matters quite a bit. So the formula changes a little bit when I'm dealing with a permutation. But the same idea, I have N things to pick from, and I'm picking R of them. And in our case, that's 3 of the 7. So let's see, 7 factorial over 7 minus 3, which is 4 factorial. And then simplify this, and I get 7 times 30, which is 210. So when order makes a difference, I have a lot more possibilities than if I deal with order does not matter. So I hope that makes a little bit of sense where order matters and does not matter.